All right, so I wanted to do a little video on this is in the book problem page 425 and just see what's happening here. All right, so we're talking about an E2 elimination, which we know only undergoes secondary alkyl halides. And we're given these two alkyl halides, okay? How do we know these are secondary? Well, our alpha carbon is the one attached to the leaving group. Our leaving group is pretty obvious here. It's this bromine that's sticking out right at us, okay? These are beta carbons, the ones that are attached to the alpha carbon. To know that this is secondary, we look at our alpha carbon. I believe you just count up your beta carbons, honestly. This carbon is attached to two other carbons, which means it's secondary, okay? Secondary alkyl halides can go under SN2 reactions, but it's telling us that this is elimination. It's telling us that this is E2, but secondary alkyl halide, we should know that that is going to be E2, okay? Usually it's also favored in a concentration of a strong base. We're not being given a reactant here, so we don't really have to worry about that, okay? What we're looking at here, let's look at this first one. So it's saying, what is the major product form when the following compounds undergo an E2 reaction, okay? So a couple of things. We know this is our leaving group, but we also know a hydrogen is going to be coming with it, okay? Not this hydrogen. It has to be a hydrogen from a beta carbon. This beta carbon doesn't have any hydrogens. It's attached to 4 carbons, right? So we know not to even look at that. This beta carbon, however, has 2 hydrogens. Perfect. We're going to take one of these, okay? Well, which one? Don't get confused and try to put these in a wedge or something. There's no stereochemistry on this one. This is not a chiral carbon. This is a chiral carbon, hence the wedge. Doesn't matter which hydrogen we take, okay? Which kind of gives you a clue that we're going to have 2 products here based on which hydrogen you take. I believe, okay? Are there any other special things that we should consider before pulling a hydrogen off? Do we have any double bonds, that would form some type of crazy conjugation? No, we don't have to worry about that. Do we have a bulky base that's going to come into play that might want to take a hydrogen that's more exposed? No, we're not even being given a reactant here, so we don't have to worry about that, okay? All right, so we know this is the beta carbon that we're working off of, and we know we're getting 2 products because this is an E2 reaction and we have 2 hydrogens on our beta carbon, okay? So what you can do here is, I kind of drew it here. We pulled our bromine off. I kept this drawn exactly where it was, okay? And because I'm making an alkene, and because we're breaking the stereochemistry and bringing everything into plane, I put this hydrogen, I just put it right here. You don't even have to draw it, but that's where it is, okay? In this case, technically, I took off this hydrogen and I kept this hydrogen here. I always try to keep the drawing how it's drawn and then lock in an alkene. And, this is the hallmark design of an alkene. So I just wanted to kind of fit into that drawing, which it is, okay? And we know that this is a transalkene because our heavy substituents are on opposite sides of the alkene, okay? We know that transalkenes are more stable, hence this is the major product. There is a minor product though. So what if we pulled off this hydrogen? What would that kind of look like? Well, I guess that's not a good example of we're pulling off another hydrogen. The way I looked at this was, let me just make this cis. Let me just turn this around, right? So I actually kept this whole thing in its same conformation. I probably could have, and it probably would have been a better example if um, I pulled this hydrogen off and I kind of pulled this down. But it doesn't really matter. If I rotated this whole thing, it would be the same thing. All I did was make a cis conformation, okay? I could do that. Let's see, if I do this and I do this, let's keep this in its same position. So let's do it, but we're not going to change what's on the right side. This is our hydrogen, okay? Let's say, okay, let's keep a hydrogen here, and our ethyl group will be here, okay? It's the same thing. I just drew the same exact thing. We have an alkene with two hydrogens on one side, okay? This tert action here, and then this ethyl group here. So it's the same thing, but this gives you a better idea. This one here gives you a better idea of, okay, instead of pulling off the hydrogen that was up here, we're going to pull off the hydrogen that was at the bottom, okay? Still gives you a cis alkene, which is less stable, and this would be your minor product, okay? Same thing, just drawn differently. Okay, so that's the first one. The second one, still an E2, this is still a secondary alkyl halide because our alpha carbon is attached to two carbons, which are the beta carbons. No hydrogens here, don't have to worry about anything over there. But look what's happening on this one. We're only attached to one other hydrogen. And this is a stereocenter, okay? So this methyl group is going into the plane of the paper, and this hydrogen is coming towards us. This is a dead giveaway because, yes, we do want to eliminate this bromine and this hydrogen, but these are right next to each other. That's no good. This favors an anti-elimination. E2 favors an anti-elimination. And remember, these are all single bonds. This whole molecule, if you make this a model, the whole thing rotates. It doesn't actually have to look like this all the time. This stuff can freely rotate, right? This bromine, if you rotated this kind of up so that this is drawn up here, your bromine would then be here, and your hydrogen would be here in the wedge, and this would be dashed, right? At any point in time, this is still going to be, I don't know if this is RS, but the conformation, the RS, the stereochemistry isn't going to change, but this whole thing can rotate. So what we want to do here is we do want to rotate this because we don't want our hydrogen and we don't want our bromine both wedged, both coming towards us. It doesn't matter what side you rotate, but what I did here was I drew out, I kept the drawing the same. Let's see what I did here. Oh, so I drew both possibilities, okay? So the first one here, I said, okay, let me keep everything on the left the same, as in the methyl was here, which is this one. And I did take the bromine from here, and because this is an alkene, I'm not going to change the drawing, I just put a hydrogen here. But that's not going to be the major product, even though this is trans, okay? That's trans. But that's not our major product, and I'm going to tell you why. I needed it to do a rotation first. And I kind of showed you here how I did this. I didn't do anything to the right side. The right side, this bromine is not in the final product. That's why I drew these in pink. The bromine is exactly where it was. It's in a wedge. But this hydrogen, I flipped this, okay? So I wanted to make this hydrogen going into the plane of paper. So I flipped this whole side. And you see how this methyl was going down and this ethyl is going, if this is my alkene, my ethyl was going up and my methyl was going down. Well, now my methyl is going up and my ethyl is going down, which would reverse the stereochemistry of my hydrogen. That's the configuration I want to make this final alkene. So this is cis, This is the major product, even though technically it's less stable than up here. We can't go through an elimination with the hydrogen and the bromine up here. That's no good. We need them on opposite planes. We need an anti-elimination, okay? So let's just double check and make sure we did this right. So the one on the left, we have our trans isomer as the major product. So that's exactly what we drew here. We have our cis isomer as the minor product. So the one that they drew is a little bit more similar to this one, but remember, these are the same thing. Okay, but let's look at the bottom. They went through a lot of confusing steps. I don't think that that was necessarily a good idea. They're like, is this R or S? Let's draw hatches. Let's draw wedges. Let's do this, and let's finally get to this. But look at their final product. Okay, I'm going to well, again, just pretend that my bromine and my hydrogen aren't here. But we have our alkene carbons. Okay, we have a hydrogen and a methyl on one side. We have an ethyl, and this, C or I'm sorry, C, CH3, CH3, CH3 on the same side as the ethyl. So we drew the same thing. That's the only product. And yes, that is in a cis conformation. See if it even says that. Because we know the configurations of the asymmetric centers, we can add the other groups. The two groups bonded to solid wedges are on the same side. Yeah, I think the way they did it was a lot more confusing. I think you just need to look at something like this and know that you need to make a rotation before you put your double bond in and lock everything into play. And remember, a double bond does not allow for rotation. This can't rotate anymore. This is all in the same plane. None of that is moving. If you make the model, you'll really see how that works. But anyway, this is E2 reactions.